Okay. Thank you, everybody, for being here. My name is Mike Spicer. I'm the lead architect for the IBM Streams product, which is a stream processing system. And what I'm going to present today is about a benchmark which we did with Walmart. The other names you see on here are my colleague, Roger Ray, who's an offering manager for us, Matt Grover, who's the architect at Walmart that we worked with on this benchmark. So this was a benchmark which Walmart did to compare a number of different streaming analytics systems, and I'll explain a little bit about what the linear road benchmark is, and also why this has anything to do with Redis, because we use Redis quite a lot with streams. When you're processing high-rate real-time streams, having a very performant in-memory key value store is extremely useful. And Redis is a particularly good one. So a little bit about Walmart and IBM. I presume that most people would have heard of both of these companies. Walmart is obviously a huge retailer. They have a ridiculous number of customers coming into their stores or using their website every single week across a large number of countries, and they employ a very large number of people. They're a very large company that do things at scale. So if they're going to pick a technology to use, they want to make sure that it'll work, and hence the rigor in doing this kind of benchmark. IBM, Big Blue, we are a global technology company. I actually came into IBM from an acquisition of Informix, and I think that was 15 years ago now. And I didn't expect there to be there probably more than 5 years. But IBM actually does a lot of pretty interesting stuff. So I've found some great technology to work on, and that's part of what I'm going to talk to you about today. So why did they do the linear road benchmark? So they wanted to be able to have a comparison of different streaming engines, and they wanted it to be something which would be agnostic. It wasn't created by a single vendor or anything like that. Something which was a full-blown, realistic, non-trivial application. There are a few benchmarks out there in this kind of area which tend to be very trivial apps, just like doing pings or very simple parts of an application. So they needed to do some rewrites to this because Linear Road, the original benchmark, was actually created back in 2004. It's created by Mike Stonebreaker and a number of people from MIT. There's a link here to an original white paper. If you just search for Linear Road and Stonebreaker, you'll find it. So this is an open source benchmark. There's elements of it which were published by MIT for doing generation, the traffic generators and the result validators. But Walmart had to update those because they were written a long time ago when things were very different. So the original systems, some of the benchmarks that they did with the original papers around this, were using kind of trigger-based systems in databases. Things have moved on a long way since that point. To give you an example, the original L rating, which they talk about this sort of L rating, which shows how much you can scale. And the example they gave was a L rating of 0.3, and you'll see later we reached something like 200. So things have changed quite a lot. So the requirements that Walmart had around stream analytics is that they want to be able to monitor all of their worldwide logistics. So, as I pointed out earlier, they're a very, very large company. This means they need to monitor things at scale. They want to be able to do inventory control and also analytics all in real time. And this is something which myself and our customers for IBM Streams, looking at real-time analytics, more and more customers are looking at taking all of their operational systems and making them real time. So, really, why do you want to know about what happened yesterday when you can't do anything about it, when if you know what's going on right now and you can affect that and change the outcome, why wouldn't you be doing that? So the technology is available to make that possible today. So a little bit of a description about the Linear Road benchmark. It's about a fictional metropolis, which is 100 miles by 100 miles, and it has expressways, and these expressways are every 10 miles. So within each of these expressways, there's an exit and an on-ramp every mile. So cars can come onto the expressways, move along the expressway for some random amount of time or distance, and then exit again. So with each of these expressways, there are 4 lanes in each direction, 3 of which are for traffic. 1 is for the on-ramp and off-ramp. And then each of these vehicles that's moving along on these expressways emits a position every 30 seconds. And then the generator for the traffic is set up in such a way that those positions actually are spread out so that they're continuously happening rather than a big burst every 30 seconds. It's just constant. But each car itself, each vehicle itself, is only emitting a position every 30 seconds. And then the other part which happens in here is that they randomly introduce accidents. So they'll have these cars moving along, and if 2 cars emit the same position with a speed of 0 in the same place, they've had an accident, and they'll stay there for some period of time until the accident is cleared. So all of this kind of takes a little while to clear, and it affects the flow on these roads. So picture on the right there just shows what these expressways look like with the on-ramps, the off-ramps, and all of that side of things. Now within this, there's a number of different types of events which can come in into the system. So the vast majority of these are these position indicators. Most of the events are saying, I am vehicle X and my position is Y and Z. Then within the events, there might be requests for historical or current information. So the first one mentioned there, type 2, is a historical request for account balances. So these expressways are toll roads. So these are just saying, what's my current balance? What's my account balance with my toll road? So if you live locally and you have a fast track, or you use public transit and a Clipper card, it's getting that kind of account balance on there. Next one is that you might ask for what was the daily expenditure, and these are more historical over the last 10 weeks. So we load up 70 days worth of history as well. The last one that's mentioned on here is the type 4, which is trying to predict what will my travel time be based on the flow of traffic. So, you'll look at how many cars are on this expressway, what speed are they moving at, have there been any accidents, and then try to predict that. There's actually another one which isn't mentioned on here, but those amongst us who can count would have spotted that type 1 is missing. And type 1 is basically an accident notification. So if you see that there's an accident, it will send out a notification saying that there's actually been an accident on the road. But this one isn't an event coming in, but this is more of a notification that's going out. Then the goal with all of this benchmark is to get the largest, what they call an L rating. So an L rating is how many of these expressways you can have. And within that, there's a criteria of you have to be able to process all this data and keep up. So there's latency requirements in terms of response times for each of these types of queries. So you're meant to respond within a second or so. So the overall architecture for this looks nice and simple. You've got a data generator, you've got the processing, and then you've got the results coming out where they get validated, and that validation step generates this L rating at the end of it. So Walmart had created an updated data generator. The previous one really couldn't send enough data for what systems are capable of now. And they'd also given a Python version of the results validator. And I'll show some links to GitHub later where all of the code for all of this is freely available. Then the piece in the middle there is that each of the different vendors, including IBM with Streams, could implement their solution to try and process the scenario that they're pushing through and see what maximum L rating they could get. So I'll show you an architecture chart in a second, but we chose to use Redis for the state which we were maintaining. We needed to keep all of these account balances, be updating tolls, etc., keeping track of all of this state. and we needed a distributed key value store. So we chose Redis for a number of reasons listed here, the maturity of it. It's remarkable to me that people seem to overlook the fact that a great characteristics of systems is that they work, and they work reliably. So Redis is great for that. We've had a lot of customer engagements where we've used Redis with Streams. The performance is very, very good. We tend to find that it performs about double similar systems. And we found that the API is very easy for us to work with, and we can do things like clustering and fault tolerance and all of those good things to make it easier for us to use. We also like the fact that you can do the memory backed by persistence. So within the Streams product, we also support checkpointing and things like this. And one of the checkpointing mechanisms that we support out of the box is using Redis as well. So as well as using it for distributed store and a cache, we can also use it for checkpointing to allow us to do guaranteed processing. And of course, it's easy to install and monitor. So this is a quick view of the architecture for the system. So we had all of the data feeder supplying us all of these position events. Those could be coming in over TCP and Kafka. And then we'd route these to the different parts of the application depending on what type of event they were. So the vast majority of them were position reports. And then we had these other effectively queries which were coming in asking for account balances and for daily expenditure analytics as well. And we'd produce the results for those. The state, as I mentioned, we were keeping all of this in Redis. So as all of this data is flowing through these different paths, we were either updating Redis or reading from Redis, and all of this was happening at a high rate. We also have the historical reference data, which was loaded up to give us the 10-week history for those queries as well. So the systems which we had to do this benchmark on, Walmart wanted this done on Microsoft Azure's cloud, and they had specific hardware which they would allow each vendor to use. I've got a little more details on that on a following chart, but this is how we set that up. So we had Streams application nodes, Streams. So this is basically where the streaming application which did all of this monitoring and the lookups and the position reports were running. We also had a management server just to take care of some of our management nodes, which do things like scheduling and basically monitoring the health of the system, being able to report on it, being able to manage jobs coming and going, which in this case were largely static, but we have those management servers there as well. And then we had basically a sort of jump box to be able to get on to the system to work with it. The specs are shown there, but I'll also show you some specs later on with a bit more detail. And we had Redis installed across these machines. So we had a cluster where we sharded the data across. And this was so that we could get more throughput and also to increase the amount of memory which we could use for the whole system. Because as we were processing this level of data, it actually builds up a lot of state. So it's actually a pretty big store in Redis there. So these were the results which we got on this benchmark. One thing, being the architect for Streams and having worked with it for a long time, one thing I'm particularly proud of is the linear scaling on this. For those that work in this kind of realm and know about concurrent systems, it's fairly obvious that if you can distribute things and you remove all contention, you can scale linearly. But not many systems do, so it's always nice when you can. And obviously being able to use something like Redis helps us with that as well. So when we were running this, we were given 4 Azure nodes to run the benchmark on. And initially we were asked to show that we could get up to 50 expressways. We got up to 50 expressways on one node. We kind of wondered what the other 3 nodes were for. We announced sort of success, and then they said, okay, well, we need you to use all 4 nodes. So they then generated more data so we could go up to 200. So you can see on the details in the top right there, the amount of CPU that we used we got up to 50 with 31%, and then we go up higher and the CPU goes down. That's because we're now using the 4 machines. So getting up to 50 on the one node, that was still only using less than a third of the CPU resources available on that node. So we then switched to using more nodes just so we could show that we would actually scale across nodes as well. The other thing you can see in here as well is the kind of rates that we're looking at. We always find it's interesting you have to level set when you're talking to people about rates, because people talk about, we're extremely high performance. And you ask them to qualify, and sometimes you get people saying we're doing millions a second, and then you're on the same ballpark. Sometimes you get people saying, we do thousands a minute, in which case we're not in the same, sort of ballpark, really. So we were running this on the one node where we were having about 1 billion events go through. This is a 3-hour run that the benchmark does. When we went up to 4 nodes, it was about 4 billion events, 400,000 a second. The other thing that the data generator does as well is it does create bursty traffic. So even though the average is at this kind of rate, it does have periods where it sends a lot more data, and you have to be able to handle that. Because the other part of the metrics which are being gathered in order for a run to qualify is that the latency in these must be very low as well. So the system which we built, the application which we built for Streams, we have a language which we call SPL, which is Streams Processing Language. We have a graphical editor, so you can drag and drop, or you can just code in whatever your favorite editor is. And the graph for the application to do this looks like a picture at the bottom there. So this was pretty straightforward for us to build. With Streams, we have a lot of, it's a domain-specific language, so it's built for streaming. Streams came out of a research project which started probably about 13 or 14 years ago. It's been a commercial product since 2009. So, we built this from the ground up to do this type of processing. So it's a relatively simple application, not that many operators. The amount of time it took to develop this is listed up there. And we have published all of this application on GitHub, so you can go look at the code. The other thing is that we have a number of what we call toolkits. I heard a lot of mention of modules, and this is kind of a similar idea and concept of pre-built functionality that you can pick up and use. So with these toolkits, we have one which is called DPS, which just stood for Distributed Process Store, because a lot of what we normally keep as state, we just keep in process memory in heap. So this Distributed Process Store includes support for Redis. So we just picked that up and used it to do part of this application. And so, it's about 3 weeks of effort of one person to do this. So it's fairly straightforward for us to do. The other thing is that when we did the scaling up for the different L ratings with the different numbers of expressways, we take this basic app, or rather this one-way sort of single app, and we have something which we call user-defined parallelism, where we just have an annotation in our code where you can just say app parallel and then how many of them you want. So we just take this one app, and for each run, we just say, okay, this one's for 200, this one's for 100. And at the point that the job is submitted, we will just basically parallelize it and spread it across the host. So the system just takes care of that for you. You have one logical definition of the flow, and then different physical executions based on what you're trying to run at the time. Here's a few more details on the different hardware which you're allowed to choose. So, we went for the first option, which had, more CPU and memory, basically, because that's really what's important to us. CPU, memory, and network. We don't tend to go to disk very often, unless somebody's using a disk-based system. Streams does all of its processing in memory. comparison to the other technologies which were tested, the other vendors that did this used Apache Apex and Apache Storm. And so you can see the L ratings that those systems got. I don't have the details on how much CPU they were using to do all of this and what the full resources being used were, but this is where they stopped. As you saw earlier on the charts, at the point that we reached 200, we still had a lot of spare capacity on the 4 nodes that we were using. One to call out in particular there is that for people who do know about stream processing, usually the system which they've heard of and use is Apache Storm. We've done a number of benchmarks against Storm where Streams is really orders of magnitude more efficient and more performant. So we can scale higher and we're way, way more efficient. So you can see we fared considerably better than Storm in this benchmark as well. A little bit of a description now which Matt had put in here, which is, or at least I think Matt and Roger put in here, which was more of an explanation around why did Walmart choose Streams, because obviously the benchmark is part of that, but there's also additional context. So this is a Forrester Wave which came out recently, which I was involved with the Forrester research team doing the evaluation. IBM came out pretty well, quite pleased with this, right up there in the top right. Interestingly enough, the one thing that we dropped some points on the current offering, so the reason we're not on the very top bar, is that we chose to integrate with stores like Redis and not to include our own store, which is built into the system. We think Redis works very well, we integrate with it, and we lost a couple of points because to score the most points, we had to have built our own and integrated it in, which I'm happy with our choices. Let's put it that way. So anyway, you can see here as well that we got pretty good comments. If you want to go take a look at this report, you can access it through IBM's website and get a copy of it. And it has a lot of details about how it did all of the evaluation and how each of the vendors answered and how they come up with this ratings. It's a very rigorous process. I've been involved in a couple now, and they really do research it properly. This is also a comparison which was done against some of the other streaming engines which they were looking at. The one area that we don't have, which is unpopular at times, is that we don't have an open source version of Streams. We do have a new open source project which is incubating at Apache called Apache Quarks, which is a stream processing engine for edge analytics. So a lot of our customers wanted to be able to run streams on edge, and that could either be in a store or on a single server in an environment where they don't have administrators, or on a small device like inside a car, on a train, on a huge piece of mining equipment. We've also have it running on phones and Raspberry Pis, these kinds of things. So we do have a open source edge analytics engine, which is built by the same team, and so using a lot of expertise. The other thing which makes a big difference for us is that we do have a lot of these toolkits, which, like I said, are kind of similar in concept to the modules. So when you use Streams, we have a lot of these toolkits which have function like geospatial, like video, like voice, all of these kinds of things just available out of the box so you can build your applications much quicker and easier. The other comparison which was made was around the price of running this system and using it. So with the benchmark results which we had, you can just see here that Apache Storm would have required 100 Azure nodes to run this. And I think that's really using just the theory that if you scale up, now the practice may be that it can't scale up to this, but let's assume that it could scale up. This is something which we've had a couple of our customers, large customer Thomson Reuters use Streams for their Icon platform, which is all of the real-time analytics piece for their news and market data. And they did a similar benchmark where they said, this free software would have cost us a huge amount of money in hardware. Similar comparison here. Then the last shameless plug slide is, you can tell that the offering manager for Streams wrote these charts rather than me, but the last shameless plug is that Streams is a very mature system. We've been doing this for quite a long time. We have a lot of big customers, and it is a very, very performant and low latency system. So it's not only being able to achieve that performance, but also in throughput, but also the efficiency with which that we do it. We generate optimized C++ code based on the usage for the application, and it really is the most optimal code we could achieve. We also have a lot of customers that have been in production for a very long time now, so it's very reliable. Something which we really like about Redis as well is that we can get that similar kind of reliability. We have a large number of these adapters, including the adapters that work with Redis. With the graphical development environment and the domain-specific language that we had, it's very quick and easy to develop applications, but also we have a large amount of metrics and monitoring information. So when you're looking at these flows, because it's a real-time flow of data just coming through, it can be very hard to figure out what's not working. So if you start to get a bottleneck or there's something that starts to go wrong, it can be quite difficult to figure out what on earth is going on. With us, we have all this information. We can give you a graphical view of it and just pinpoint where bottlenecks are, etc. Even though we're not open source, we do have quite a large number of our toolkits are available on open source on GitHub. We also have an open forum, and we do have a developer edition, which is no cost to use as long as you're not in production. So really, we just ask that at the point you're in production, that you contact us and pay a license. We have a lot of advanced analytics. One of the good things about being inside IBM is that there's a lot of different groups with a lot of interesting analytics that we can pick up. So we have a really very broad range of analytics. A lot of those are either in the box or they're out on GitHub to pick up. And obviously, we are an enterprise kind of company, so we've done a lot of the enterprise integration as well. So lastly, and I've realized I've gone through this fairly fast, but hopefully that's brevity and conciseness are good in my book. So if you want to take a look at more of this, there are these links here. So the Streams product, like I said, you can get a download as a VM or a native install on Linux and use it in development for free. And then, if you want to use it in production, we would ask that you pay a license. There's also the areas on GitHub where this linear road benchmark is published, both the generators and the evaluator code from Walmart, and also the benchmark from Streams. And then within this IBM Streams area, there's also a number of different examples and samples, and also these open source toolkits that you can use with Streams. And then lastly, we do have a developer community. So there's a forum there where you can ask questions. We've got lots of examples and samples there. And so, I hope that you are interested enough, based on this talk, to go take a look at it. And that's it. Thank you. I'll be happy to take any questions if people have them. Thanks.
Hi, thanks for the talk. That was really helpful. So when you're using Streams, actually, within the Streams, processing engine, do you have any workflow that is within the Streams that will process the streaming, messages or events? And also, do you also keep track of states of each of the workflow that you have created? And also, do you spool them, or do you actually keep them, persist them in the persistent storage?
Okay, so I think I heard 3 questions. So the first one was, can you write something to process all of these events? Yes, I mean that's what this benchmark was. Is that Streams itself is a general platform for doing this kind of stream processing. We have all of these different operators and toolkits which have pre-built function, and then you can write an application which uses these and uses any additional pieces which you want to do to build an application or a flow, which might look something like this picture at the bottom. So in this flow, the events are coming through here, and I think actually, in this particular one, the ones up here, I think, were the input of Kafka and TCP. Then they were coming in and being routed to the different places based on the type of event. I think this one was the daily expenditures. This one was tracking toll notifications. One was producing accident notifications. So it's a framework for building those kind of applications. So in addition to SPL, we also have the ability to write these flows in a functional flow language or API, which we call a topology API, and that can be done either in Java or Scala or Python. And if any of you are familiar with something like Spark streaming, it looks very similar to that. Here's my stream, here's an operation on it, and you just sort of chain all of those along. Now, you asked about state and do you spool them. So in this particular example, we were using Redis to keep state, but we also have state which is local to the operators, and we have the notion of windows. We have very rich windowing semantics, so you can say they're tumbling windows, sliding windows. You can say how big the window is, and then how often it should trigger to do a calculation on the window. All of these kind of things are supported as part of the language and runtime. And now I think I've forgotten your 3rd question, but I'm sure there was one.
I think I even forgot what I asked.
Okay. Well, I think you asked if we spooled them or something. In general, we keep things in memory, but if we do need to if it goes beyond that, we would use something like Redis and be able to spread it out onto more hosts. Okay. Or we can work with stores and messaging systems. So it really depends on the application, but it is a generic platform for building these kind of things.
And so have you actually done any implementation with the Hadoop as well?
Yeah, most of the customers that use Streams use it in conjunction with warehouses, messaging systems, data lakes, Hadoop, Spark. Invariably, what's happening then is that they'll use those data stores to generate a model, like a predictive model. And then, that might be saying that, this customer is most likely to buy this, or this customer is most likely to churn for telcos. And that calculates that model. And that's useful at some level to say, okay, well, now we understand why we're losing customers. But what's much more effective is if you can score that in real time on the stream and then affect the outcome. So, for example, we work with a large telco that scores, they build models on a Hadoop system, then they score over 500 models in Streams on a huge number of events where they've built up context on 60 million customers, and we score and affect the outcome within 8 milliseconds for the full processing of that. So it's used for targeted advertising. So somebody's interacting with them through multiple channels. We keep track of the fact that even though they came in through multiple channels, it's this one person. We have these models which we use to score and predict what advert we should offer them, what offer we should offer them. And then all of that is pulled together that as they move through a website or a TV system, it will join all the dots and say, do this next. And that'll happen while they're doing that interaction. So that 8 millisecond latency is key for really changing the outcome. Yeah, so it's not about sort of doing an autopsy of what went wrong. It's about making it go right the first time round. Thanks. Any other questions? Thank you.
Sorry, I had a quick question.
Oh, okay. I was like, where's that voice coming from?
On the Apache Storm, for the Apache Storm group, were you involved in building the system that they benchmarked at 10Ls?
No. So each of those results which were presented were done by the vendor that was responsible for them. We have done a benchmark with a customer of ours, a very large customer of ours, who was a government customer who was under pressure to use open source unless they could justify it. And we've published the results of that a number of years ago. And we wrote a paper on it. We published all the code for it. Basically, so we're trying to be transparent. This is everything we did. We want to be open. If somebody can make it run faster, have at it. And to the best of my knowledge, nobody has tried. With this particular benchmark, Walmart went out to a number of vendors and asked, do you want to compete? I do know who the vendor was behind Storm, but Walmart haven't made it public, so I don't wish to state it. But it is somebody who is very, very familiar with Storm and would have done the best they could. Yeah, I feel very awkward about dissing other people, but these are numbers, these are facts. We've published everything. Go take a look. That's my British half coming out. That couldn't possibly be nasty. But I am proud of what we've done. So. Okay, thanks very much.